Let's move on to subspaces now. Keeping in mind that V is the entire space from negative infinity to infinity in R3, let's figure out what the subspace of R3 would be, and we'll call that W. We're going to have to define W as being a subset of V, so we're going to pull some vectors out of V, and we're going to call it V1, V2, and V, who knows how many. It could be infinite numbers. Let's remember that we can mathematically represent that we took V1, V2, and V however many we wanted to, but they were all elements of our original vector space V. Clearly, a subspace is going to contain infinite vectors. A shorthand way of writing that W is a subspace of R3 is to just say that all this stuff right here is a subspace of R3. What this means is we're still in R3. So that means that any vector in W is going to have to be represented by some 3D vector. So all the vectors in W are represented by question mark, question mark, question mark. If this is the case, and knowing that we have to still follow those three rules, let's see what types of subspaces we can form. The first one is going to be called a trivial subspace, because it's literally just going to be only the zero vector. And that's it. And we know that the dimensions of the zero vector is going to be 0. Another type of subspace that's going to follow the rules is going to be just a line, specifically a line through the origin. And that's going to look something like there's the origin, something like this. Another type of subspace is just going to be a 2D plane. So that's just going to look something like this. The X and Y plane, for example. It could also be that subspace W represents the entire R3 space. So it could be for these vectors that all of the entries in the vector are non-zero, and so you're just going to get the entire R3 space, even though it's a subspace of R3. Remember that this symbol says less than or equal to R3, so we can calculate the dimensions of the W subspace by saying it's the number of basis vectors in the subset. We've mentioned basis vectors a few times. Let's define a set of basis vectors B. That's just going to be similar to saying like B, and let's imagine a sub I, a B sub J, or B sub K. For any 3D space, usually these basis vectors are just going to be I hat, J hat, and K hat, which are going to have a magnitude of 1. If we wanted to use these three basis vectors for the subspace W, then we have to say that we took BI, BJ, and BK from the subspace W. These basis vectors have to follow really important rules. Number 1, they must be linear independent. Number 2, the basis vectors also span a k-dimensional subspace of R to the k or greater space. Let's try to make sense of this statement by writing W is equal to the span of, let's start with just two vectors, so BI and then the BJ, and then if we do that, we're going to have to say that it's a subspace of R3. So we see that it's actually a two-dimensional subspace of R to the 3 space, because we have the dimension of W is equal to the number of basis vectors 1, 2. In this case, we do have 3 basis vectors, so we can claim that W is actually a subspace of R3, but notice that it's a 3-dimensional subspace. And so if that's the case, we can actually set that equal to R3. Just remember that it wasn't the case when we had 2 of these. We couldn't just set that equal to R2. We can only do that if the subspace is equal to the same dimensions as the whole space. The C's are the coordinates in front of the basis vectors, and so we make that calculation, we're going to get some V sub question mark, because we don't really know which one it is. Is it the first vector, the second vector, third vector? We don't know which vector it is, but it's going to be some vector. As long as the V question mark, that vector, is a part of subset W. Since these basis vectors came from set B, let's call this the B coordinate vector of subset W. And we could rewrite this another way. We could say that if we wanted to find vector V, we'd have to use some sort of a basis B And then we'd need to find a coordinate along with that basis. And the coordinate is just going to be C1, C2, and C3. So if we use those coordinates with the basis B, we're going to get vector V out of it. This also means that we can take our matrix B, let's say we loaded these 3 basis vectors into a matrix, and we can multiply it by this vector that we found, V sub B, that coordinate, the B coordinate vector. And then we're just going to get V right back out of that. Now it's important that we try to eliminate any extra V question marks that we find in set B. Because the truth is, if we take the span of BI, BJ, BK, along with some other V that we formed using BI, BJ, and BK, then that's simply going to be equal to the span of BI, BJ, and BK. So we really didn't need this V question mark. So our goal is to eliminate those extra V question marks. A clue that there might be an extra V question mark somewhere is if you take 1 times BI plus 2 times the BJ plus 3 times the BK, and then you somehow have like a minus 4 times some V question mark, that equals 0. You can rearrange this and you'll note that these 3 are equal to 4 of these, and so now you know that there's an extra V question mark. Let's now define C as column space. And so if we were to try to take the column space of matrix A, then we would see that that's just simply going to be equal to the span of A1, A2, and then A sub n. But that's also going to be a subspace of R to the power of m, which makes sense. What this is saying is it doesn't really matter how many number of columns you have. This the span of the number of columns is still going to give you some subspace of the number of rows that you have. So the rows are kind of telling you how big the space is, and the number of columns just are telling you how many vectors you combine together. Let's make a quick note that if we wanted to find the dimension of the column space of A, we would just have to figure out what the rank of A is, and that would just tell us the dimension of the column space. Let's also define the null space. It has a big name, but it just means that we're taking the set of all possible x's that satisfy the equation where ax equals 0. These two spaces are somewhat opposite, so if we know that the column space of A is a subset of R to the m, then we know that the null space of A is actually a subset of R to the n. Now there's a really important theorem that states that we can find the dimension of the null space A by finding n, which is just simply the number of columns, and then subtracting the rank of A. So we could see the relationship between the null space and the column space with this equation here. Let's say we wanted to find the basis for the column space A. In order to do that, we have to look at A, and then we have to find and pull out the basic pivot columns from A. Well, let's look at our matrix A, and let's find our pivot entries, which are going to be here, and here, and here. And we're just going to take those columns, this one, and this one, and we're going to build the column space A. So let's write that the basis for column A is going to be equal to 1, 0, 0, 2, 1, 0, and 4, 3, 1. Those are 3 linearly independent vectors that are going to form the basis for column A. Well, what can we say here? First, we can say that the column of A, the column space of A, is going to be a subset of R to the third. Also, we know that the rank of A is simply equal to 3. You could see it's already set up that way. And so we can say that the dimensions of the columns of A is equal to 3. In this case, we can see that the column space C actually spans the entire r to the third space. Let's now consider the basis of null A. In order to do that, we have to solve the equation ax is equal to 0. We have to find all the x's. Well, let's figure out what x is, all the x's. There's a whole bunch of x's. Usually we just say x, but I'm going to claim that it's x1, x2, x3, x4, and x5. All those exist inside of the vector x, right? So that's going to be equal to, we have 1, 2, 3, 4, 5 x's. We're going to use the third one here, so we're going to say x3, and then we have to multiply it by some kind of a vector. In order to make these dimensions consistent, we're going to have to use 5 entries in here. So 1, -2, 1, and 0, and then 0. And here we can add that to, let's use x5 over here. So x5, and then that's going to need 5 entries as well. So 0, -1, 0, -2, and 1. And now we've seen that we've found the basis of null A. So let's say that the basis of null A is simply equal to 1, -2, 1, 0, 0, and then we have 0, -1, 0, -2, 1. That's going to be the basis for null A. Well, what can we say about the null space? We could say that the null of A is a subspace of r to the 5. So we have r to the 5 in this case. However, this was built on 2 free variables. And so it turns out that the dimension of null A is equal to 2. And we can use this. We can say 5 minus the rank of A. What's the rank of A? Is 3. So 5 minus 3 also gets you 2. And in this case, we could say that N, the null space, spans a 2-dimensional subspace of r to the 5 space. Let's try a little example with changing bases. We're going to establish 2 bases, I and j. We can see that I is the standard basis and j can actually be formed from the standard basis. Well, how do we form the vector j1, which is simply going to be 2, 1? In order to form 2, 1, we needed 2 of the I1s, right? And then we also need 1 of the I2s. And if we do that, then we get 2, 1. We could also say, how the heck can we get 1, 3? That's going to be j2. Well, all we needed to do that is we needed 1 of the I1s, and then we needed 3 of the I2s. And so those 2 expressions are the same. We can rewrite this a little bit. We're trying to achieve j1. And we're trying to achieve j1 by using the I basis over here. So if we were to do that, let's think about it. We're trying to form the vector 2, 1 by using this. We're going to need the coefficients to be 2, 1. So let's set up the vector here being 2, 1. Those are the coefficients that we need to form j1. Let's also rewrite that for j2. Say if we're trying to form j2 using the basis I, in order to do that, we're going to need some coefficients over here. Well, how do we form j2, 1, 3? Well, we're just going to need 1 and 3 of our standard basis, and it's going to form j2. Well, these vectors 2, 1 and 1, 3, we wrote them using the basis I. But let's say we wanted to write them using the basis j. In order to do that, let's try to set it up like this. Let's say that we can try to find j1 using the basis I, which is going to be equal to 2, 1, right? But we're trying to rewrite that using some new coordinate system, x1 and x2, but this time it's going to be from the basis j. Now we can eyeball that. We could say that 2, 1 is going to be equal to, what does this require? It requires 1 of those and 0 of those. So we found that x1 is 1 and x2 is 0. We do the same thing for the other vector. We were trying to represent 1, 3 using the basis I. So let's say we were trying to represent 1, 3. We could just say that j2 sub I, that's just equal to 1, 3, right? So how are we going to represent 1, 3 with the basis j? We're going to need to use some other coefficients. We'll call it y1 and y2. And this time we're going to use the basis j. So if we're trying to get 1, 3 from the basis j, we know that the y's are just going to need to be 0 and 1. So we got 0 and 1 for the y's. Now let's consider this equation right here. Let's try to multiply this j1i by an I from the left side over here. I, well, that'll just give us J1, right? We could do the same thing for the other one. Let's take this J2 sub I. Let's just multiply that from the left by I. And if we do that, we're just going to get J2. Okay, so now let's try to factor this out a little bit, because we could say that this is just going to be equal to like I, and then let's put all this together. So we have like J1, J2 sub I. And so we're multiplying the I by some matrix here. And then that's just going to be equal to all of these together. So we would have just a big long matrix, Ji, J2, and there we go. Here we can rewrite this again, and we could say now that we have a matrix I, and then we had to multiply it by something over here. I'm just going to call this J1, J2 sub I thing, I'm going to call it A, and then I'm going to say that it goes from J back into I. There's a little arrow right here. But that's the matrix that is going to translate these i's multiplied by something gives you over here on the right, it's just a J matrix. So we had to multiply matrix I by some matrix to get the J matrix. Well, we can see that this A, J to I matrix is equal to J1, J2 sub I. But I'm going to write it like this, a little big bracket right here. And then I'm going to take the first one, J1, and we're going to call that sub I. Then we take the second one, which is J2. I'm going to put that sub I. Now we can see we can easily make the A, J to I matrix if we already know, basically from step 1, what those particular vectors are. We're going to call this matrix right here the change of coordinates matrix, and of course it is also linear independent. The purpose of this matrix is to be able to translate things that are in a sub J into a sub I. So let's say we wanted to take, for example, the vector J1 that was in the sub J. In order to create J1, which is just 2, 1, from the J basis, all we need is to just get a 1 and a 0. If we plug in a 1 and a 0 here, we get J1 using the J basis. Now this matrix here, A, J to 1, is going to be 2, 1, 1, 3. So let's go ahead and put a 2, 1, 1, 3 over here. So if we multiply these two things, well, the idea is that over here, we're going to get another J1, but this time it's going to be of the sub I. So we're able to translate something from sub J into something sub I. So does this hold? If we multiply this matrix by 1, 2, on the left here, we're just going to get the vector 2, 1. And let's ask ourselves, is J1 sub I equal to 2, 1? Well, it sure is. So that matrix works. Let's return back to our spaces, and let's try to find some bases for these spaces. So the basis for R, is just going to be 1. That means that whatever x we put in here, we basically have that coefficient x, and we're going to multiply it by 1. So the coefficient x could be, I don't know, 0.6. And you multiply 0.6 by 1, you're just going to get 0.6. So that's the basis for R, is just 1. Look at the basis for R3. If we wanted to find a basis for R3, that's just going to be equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is a basis. This isn't the only basis. But this basis will work pretty well because we can plug in any number in here, and then we could sort of get this whole like x times this one, y times that one, and a z times that one. You add them all up, and you're just going to get one vector over here. The basis for P2 is going to be a little bit more interesting. We're going to require 1t and then a t squared. And then from there, we can multiply that by something A, B, and C. And when we do that, that simply yields us this whole expression that we have A plus B, and then there's a t squared here, or just a regular t, and then we have a plus the c with the t squared. And that'll give us all these polynomials. We required this basis here, 1t and t squared. And so the big idea here is that we're able to take any of the vectors that lie in one of these vector spaces, and you can form them by using the basis of that vector space times the coefficient that is required to build that vector within the space.